Welcome, curious learners, to the deep dive. I'm really glad you're here with us today because we're jumping into a topic in artificial intelligence that's, well, it's really starting to change things.
It really is. We're moving beyond AI that just, waits for instructions.
Exactly. We're talking about AI that doesn't just passively follow commands. It anticipates what you might need. It can make decisions all on its own. And this is the big one, it learns and adapts.
Yeah, forget the simple chatbots or the voice assistants that just kind of react to what you say right now.
Right. This is different. We are taking a deep dive today into the world of agentic AI.
And it genuinely feels like the next big step, doesn't it? How AI fits into our world, how it influences things. It's this shift from AI being just a reactive tool.
Waiting for orders.
Yeah, waiting for orders to becoming more like a dynamic, proactive partner, something that can actually take initiative.
So if you're curious about where technology is heading, how AI is evolving out there in the real world, understanding agentic AI isn't just like interesting trivia.
No, it's becoming absolutely crucial. You really need to get a handle on it.
That's spot on. So our mission for this deep dive is pretty straightforward.
Yeah.
We want to unpack what agentic AI actually is. How is it fundamentally different from the AI systems maybe you're already familiar with?
And what are the core pieces, the foundational components that make these, sophisticated agents work?
And why is this specific kind of AI becoming so vital so quickly across so many different industries? It's popping up everywhere.
Think of this as like your shortcut to getting really well informed on this. We'll try to pack in some surprising facts, maybe a little bit of humor, keep things moving.
We hope so. And remember, we're tailoring this for you, the curious learner. The goal is clarity, real understanding without drowning you in jargon or overwhelming detail.
Yeah, we want to guide you through it, so hopefully you have those moments where it just clicks, those aha moments when the abstract stuff suddenly makes sense.
Okay, so settle in, maybe grab a coffee or tea, because we're about to explore some really fascinating territory here, right into the heart of autonomous intelligence. Let's unpack this.
All right.
So to really get to grips with agentic AI, we probably need to start with the basics. What exactly is an AI agent?
Right. Good starting point. At its core, an AI agent is basically an autonomous entity. It's designed to do two main things. First, perceive its environment, sense what's going on around it.
Okay, proceed.
And second, based on that perception, act upon that environment to achieve specific goals it's been given, or maybe even goals it sets for itself.
So the emphasis isn't just on reacting to things.
No, not at all. It's really about proactive, goal-oriented behavior. It's not just sitting there waiting for you to spell out every single step. It's empowered to take some initiative.
And that proactive, goal-oriented piece, that's why these agents are becoming so important, right?
Right. Absolutely. Their importance, their relevance, it stems directly from that ability to automate really complex tasks. Tasks that would normally need constant human oversight.
Which means more efficiency, I guess.
Huge improvements in efficiency, yeah. But also, maybe more importantly, they can tackle problems that go way beyond simple rule following. If this, then that.
Right. Traditional programming.
Exactly. These agents are designed to navigate and respond to situations with a degree of independence, dynamic adaptability. Things that older, more rigid systems just can't handle. They're built for a world that's messy and constantly changing.
Okay, so that difference between just reacting and being proactive, that leads us nicely into the defining characteristics of agentic AI. And the first one you mentioned, autonomy, feels like the big one.
It really is fundamental.
Uh-oh.
Autonomy. When we talk about an AI agent's autonomy, we mean its ability to operate independently. It doesn't need constant external control. It doesn't need a human checking in for every single decision or action.
So it's not just following a script.
Not at all. It's not just executing pre-programmed instructions step by step. Instead, it uses its internal state, what it currently knows or believes its knowledge base, and its reasoning abilities to make its own decisions,
Okay.
and that it initiates actions and pursues its goals based on those decisions. This means it can, dynamically adapt what it's doing on the fly to reach its objectives, even if the situation changes unexpectedly.
And you mentioned it's not just like on or off, right? Autonomy isn't binary.
That's a crucial point, yeah.
Yeah.
It's definitely not binary. Autonomy exists on a spectrum. There are varying degrees. How much autonomy an agent has depends on how it's designed, how complex its environment is, how critical its tasks are.
So some might have very limited freedom.
Exactly. On one end, you might have an agent with very limited autonomy, maybe only making simple, predefined choices within a very narrow scope, like maybe a thermostat that just decides between on and off based on temperature. But on the other end of the spectrum, you've got systems showing incredible self-direction. They're capable of really complex planning, adapting to highly dynamic, unpredictable environments, much more sophisticated.
Can we make that more concrete? An example might help bring autonomy to life?
Definitely.
Yeah.
Let's take a really powerful real-world example,
Mm-hmm.
the self-driving car. That's a prime illustration of high autonomy in action.
Okay, yeah, we hear a lot about those.
Right. So a self-driving car doesn't need you, the passenger, constantly telling it, okay, accelerate now, brake, turn left here.
Obviously.
It autonomously navigates roads,
Yeah.
uses its sensors, cameras,
Mm.
LiDAR,
Mm.
radar to sense its surroundings.
Yeah.
It identifies and avoids obstacles, pedestrians, other cars. It makes complex, real-time decisions about speed, lane changes, all based on traffic laws, conditions.
And it plans the route.
Plans the whole route from A to B. It even tries to anticipate the actions of other drivers or pedestrians by predicting what they're likely to do next. It adapts smoothly to changing traffic, sudden
Yeah.
jams, accidents, and, maybe most critically, it learns from its experiences. It's constantly refining its driving skills based on millions of miles, whether simulated or real.
So that whole cycle sensing, planning, acting, learning, that's high autonomy.
Exactly. It sets goals, like getting to the destination safely. It formulates and executes plans, navigating the route. It learns from new data, and it acts without needing constant human input. It's this continuous, independent decision-making loop in a very complex environment.
Okay, that makes sense. So beyond autonomy, what's another key characteristic that really sets agentic AI apart?
The next big one is proactivity.
Proactivity, okay.
Proactivity is the agent's ability to take initiative, to act in anticipation of future needs or opportunities rather than just reacting to what's happening right now.
So it's looking ahead.
Exactly. A proactive agent doesn't just sit back and wait for things to happen to it. It actively seeks out information. It might set its own intermediate goals or sub-goals, and it plans actions to achieve those goals with a kind of forward-looking perspective. It's about foresight, taking charge, not just responding.
Okay, so maybe help clarify the difference there. Reactive versus proactive.
Sure. Imagine a simple system, maybe a thermostat again. A purely reactive thermostat turns the heat on when the temperature drops below a set point. It's a direct response to a current stimulus.
Mm-hmm.
It's cold now.
Right.
A proactive system, maybe a smart home agent controlling that thermostat, might turn the heat on before it gets cold. Perhaps it checks the weather forecast, sees a cold front coming, knows you usually get home around 6 p.m., and starts warming the house at 5:30 p.m. so it's comfortable when you arrive.
Ah, okay. It's anticipating.
It's anticipating the need based on future predictions and learned patterns. But as you hinted earlier, reactivity is still absolutely essential for agentic AI. It needs both.
Right. It can't just be planning for the future and ignore what's happening right now.
Precisely. While proactivity is about looking ahead, reactivity is the agent's ability to respond directly and immediately to things happening now in its environment, especially unexpected things. And we can even break down reactivity a bit. There's something called reflexive reactivity. These are immediate automatic responses, almost like reflexes, no deep thought required. Think of a robot arm working on an assembly line. If its sensor detects an unexpected object in its path, it might retract instantly. That's a hardwired safety reflex.
Okay. Simple reaction.
Then there's deliberative reactivity. This is more sophisticated. The response is still based on the current situation, but it involves more complex reasoning and planning in real time. Think of a high-level chess-playing AI. It's reacting to your move, but it's not just a reflex. It's analyzing the board, considering possible future moves, evaluating strategies, and then choosing its best response. It's reacting, but with deep, deliberative thought.
Got it. Reflexive is instant. Deliberative involves thinking. So we have these three core ideas: autonomy, proactivity, and reactivity. Can we tie them all together with maybe one core analogy, something relatable?
Yeah, let's use smart home automation. That's something many people are starting to experience.
Okay, good one.
So think about a very traditional, maybe first-generation smart home system. It lets you control your lights, maybe your thermostat, but only when you explicitly tell it to. You use a voice command, "Hey system, turn on the living room light," or you push a button on an app.
Right. I tell it what to do, it does it.
Exactly. That's a purely reactive system. It just sits there, waits for your command, and carries it out. No initiative, no learning, no foresight.
Okay, that's the baseline. Now contrast that with an agentic smart home system.
Right. This system is different. It would continuously learn your preferences, your daily routines, maybe even track who's home and who isn't. It also adapts to the external environment.
So how would that work in practice?
Well, it might proactively adjust the thermostat, not just based on the current temperature inside, but maybe using the long-range weather forecast for the day. It knows you like it cooler when you sleep, so it starts cooling the bedroom before you even head upstairs.
Okay, anticipating again.
It could automatically turn on specific lights, maybe pathway lights, as you walk into a room or approach the house, anticipating your presence based on your phone's location or motion sensors.
Yeah, that's handy.
It might even get into things like managing your supplies. It notices, maybe through smart fridge sensors or just tracking your grocery lists, that you're running low on milk or coffee beans. It could proactively add them to your online shopping cart.
Or even order them.
Or potentially, yes,
Yeah.
even place the order itself if you've given it that level of autonomy,
Hmm.
especially when supplies hit a critical low point.
Wow. Okay, so that system is...
It's truly autonomous because it's operating and making these decisions without you constantly telling it what to do.
Hmm.
It's proactive because it's anticipating your needs, comfort, lighting, groceries, and acting on them ahead of time. And it's still reactive because if something unexpected happens, like a sudden unforecasted heat wave, or maybe a guest arrives unexpectedly, it can sense that change and adjust its behavior immediately.
That blend, that's the key.
That blend is exactly where the power lies. It's not just a slightly smarter gadget. It's a fundamental shift.
Mhm.
Technology moves from being a passive tool you command to being a more dynamic learning collaborator that tries to anticipate and adapt with you.
That really does crystallize the difference. And I guess we can apply the same comparison elsewhere, like maybe in business.
Absolutely. Let's take inventory management in, say, a large retail warehouse. A traditional AI system might be really good at predicting demand for a product.
Okay, forecasting.
Yeah, based on historical sales, seasonality, maybe even current events or marketing campaigns. It could tell a manager, okay, based on our analysis, you'll likely need 500 units of this widget next month.
But someone still has to act on that prediction.
Usually, yes.
Mhm.
Human manager typically reviews that forecast, uses their judgment, maybe checks other factors, and then manually places the purchase orders with suppliers. The AI predicts, the human acts.
Got it. So the agentic version.
An agentic AI system for inventory management would take it much further. It wouldn't just stop at the prediction. It would autonomously manage the whole inventory lifecycle.
End to end.
Pretty much.
Oh.
It predicts the demand, monitors real-time stock levels, tracks incoming shipments, maybe even monitors supplier reliability, and then based on all that, it automatically places orders when stock falls below an optimized threshold.
So it's doing the ordering itself.
Yes.
Yeah.
Might even go further. Maybe it dynamically adjusts pricing on slow-moving items to clear out excess inventory. Or it could optimize where products are physically stored in the warehouse to minimize the time it takes for robots or humans to retrieve them for shipping.
So it's sensing, planning, and acting across the whole process.
Exactly. It's a continuous automated loop. Sense market conditions and stock levels, forecast needs, plan optimal inventory strategies, and then directly take action by interacting with ordering systems, pricing systems, maybe even warehouse robotics. Full cycle automation.
Okay, one more analogy that you mentioned earlier really caught my attention. Personalized education. How does this agentic idea apply there?
Ah, yes, this is a fascinating area. So a traditional AI tutor, maybe like some online learning platforms you use now, might give you recommendations based purely on your past performance.
Like, you got this quiz question wrong, so here's another video on that topic.
Exactly. It looks at your scores, identifies weaknesses, and suggests remedial material or practice problems. It's helpful, certainly, but it's somewhat limited to just your explicit performance data.
Okay, so the agentic tutor.
An agentic AI tutor aims for a truly personalized, deeply adaptive learning experience. It goes much deeper. It would continuously monitor not just your quiz scores, but maybe your engagement levels. How quickly are you answering? Are you rewatching videos?
Even emotional state.
Potentially, yes. Through analyzing interaction patterns, maybe even webcam input with appropriate consent, it might try to infer if you're getting frustrated or bored or feeling confident. It would try to understand your individual learning style. Do you respond better to visual explanations, text, interactive exercises? And it would keep your long-term goals in mind.
And how would it use all that information?
It could adapt its teaching style in real time. If it senses you're struggling with a concept explained through text, it might switch to an interactive simulation or a video explanation.
Wow.
If it detects your motivation seems to be dipping, maybe you're taking longer breaks or getting things wrong you previously knew, It could offer encouragement, or perhaps suggest switching to a different topic for a while. It could even dynamically adjust the difficulty of the entire curriculum, making sure you're constantly challenged but not totally overwhelmed.
That feels much more like a real tutor adapting on the fly.
It really pushes the boundaries of what a digital learning companion could be. And it raises some really interesting, maybe even profound questions, doesn't it? Like, how much can or should an AI truly understand and support a human learner on such a personal, nuanced level?
Hmm.
Where do we draw the line between helpful assistant and, well, something else?
That's a big question for sure. So, okay, we've established what agentic AI is, why it's such a leap forward, moving from reaction to proactivity and autonomy. But the real magic, or maybe the engineering, is in the how. How do these things actually work? Let's pull back the curtain a bit.
Right, let's look under the hood. The fundamental framework, the basic operating cycle for most intelligent agents, especially agentic ones, is often described by what we call the Sense Plan Act loop, sometimes called SPA.
Sense, plan, act. Okay.
It's exactly what it sounds like. It's a continuous iterative cycle that defines how the agent interacts with its world. First, the agent senses its environment, it gathers information. Second, it plans a course of action based on its goals and what it just sensed. And third, it acts by executing that plan.
And this loop just repeats.
Constantly. Sense, plan, act, sense, plan, act. This continuous feedback loop is the absolute foundation for allowing dynamic, adaptive, intelligent behavior in a world that doesn't stand still. It's always observing, thinking, and doing.
All right, let's break that down, starting with sense, or I think the term in AI is perception.
Exactly. Perception. This is the agent's ability to gather information from its environment using various sensors and then, crucially, interpret that information. It's not just about collecting raw data streams, it's about making sense of that data to build an internal representation, like a coherent model of the world around it.
Why is that internal model so important?
Because that model is what the agent uses to understand its current situation, predict what might happen next, and ultimately decide what to do. Without a reasonably accurate model of the world, its planning and actions would be ineffective or even dangerous.
Okay, and what kind of senses are we talking about? What are the sensors?
Oh, they can be incredibly varied and sophisticated. Cameras are a big one, obviously. They act as the agent's eyes, capturing rich visual data. This lets an agent do things like object recognition, identifying cars, people, stop signs for a self-driving car.
Scene understanding.
Yeah, understanding the overall context of a scene, navigating complex spaces. Then you have depth sensors, like LiDAR light detection and ranging or simpler infrared sensors. They measure distances to objects very accurately.
Crucial for not bumping into things.
Absolutely essential for obstacle avoidance and also for creating detailed 3D maps of an environment. Think robots navigating warehouses or autonomous vehicles mapping roads.
What about other senses? Touch.
Yep, tactile sensors. These detect physical contact, pressure, texture. Imagine a robotic hand needing to grasp fragile objects, or even a surgical robot needing to feel the tension in tissue. Tactile sensing provides that crucial feedback. And then there are proximity sensors. These detect nearby objects without physical contact. Think of the automatic doors at the grocery store that open when you approach. Or maybe warehouse robots, using them to maintain safe distances from shelves or each other. They sense nearness.
It's amazing how many different ways an AI can sense its world. And in something like a smart home, it's probably using a whole bunch of these, right?
Totally. What's really interesting in the smart home example is how everyday devices become the agent's sensors. Your standard temperature sensors and thermostats, light sensors measuring ambient brightness, motion detectors figuring out if rooms are occupied.
Door and window sensors.
Yep, indicating if they're open or closed. Maybe air quality monitors, water leak detectors in the basement, security cameras providing visual feeds. All of these are constantly feeding streams of data into the central agent.
Giving it a very complete picture.
A really comprehensive, real-time picture of what's happening in its environment. Far more detailed and continuous than any single person could possibly monitor. These sensors are literally its eyes and ears spread throughout the house.
But that raw data, it's probably not perfect, is it? It must be messy sometimes.
Rarely perfect, yeah. Raw sensor data is often noisy, meaning it has random fluctuations or errors that aren't part of the real signal. It can be incomplete, maybe with gaps where a sensor temporarily dropped out, or it can be inconsistent, perhaps different sensors reporting slightly conflicting information.
So you can't just feed that raw mess straight into the planning part.
Exactly. That's why data preprocessing is such a vital first step within the perception phase. You have to clean up and prepare the data before the agent can reliably make sense of it. It's like tidying up your workspace before you start a complex project.
What kind of cleaning techniques are used?
Several common ones. Noise reduction is key. This involves using mathematical techniques like smoothing filters or more advanced methods like Kalman filters to estimate the true underlying state from noisy measurements. Kalman filters are great for tracking moving objects, like in radar systems.
Okay, filtering out the junk. What about gaps?
That's where missing value imputation comes in. If you have gaps in your data stream, you try to intelligently fill them in. Maybe you predict the missing value based on the values before and after it, or use statistical averages or more complex predictive models.
And weird data points, outliers.
Good point. Outlier removal identifies and often discards data points that are statistically very unusual or inconsistent with the rest of the data. These outliers could be due to sensor errors or rare events, and they might otherwise skew the agent's understanding. And one more important technique, especially for training the AI models involved in perception, is data augmentation. Here, you artificially create more training data from your existing data by making small, realistic changes, like slightly rotating, scaling, or changing the brightness of images. This helps the AI learn to be more robust and generalize better to slightly different situations it hasn't seen before.
So after all that cleaning and augmenting, what's next in perception?
After pre-processing, you typically move to feature extraction. This is where the agent identifies and pulls out the most important relevant characteristics or patterns from the clean data. For example, in image processing, features might be edges, corners, textures, or specific shapes that help identify objects. It's about focusing on the meaningful parts of the data.
So a quick question then. What happens when an agent has lots of different sensors, like the self-driving car with cameras, LiDAR, radar? How does it combine all that information?
Great question. That brings us to sensor fusion. This is a really sophisticated and critical process. It's all about combining data streams from multiple, often different types of sensors to create a single unified understanding of the environment that is more accurate, more complete, and more reliable than what any single sensor could provide alone.
So the whole is greater than the sum of its parts.
Exactly. Think about the self-driving car again. The camera is good at recognizing signs and colors. LiDAR is excellent at precise distance measurement and mapping. Radar works well in bad weather, like rain or fog, where cameras and LiDAR might struggle. Sensor fusion intelligently combines the strengths of all these sensors, often using advanced techniques like, again, Kalman filtering or Bayesian methods, to weigh the reliability of each sensor's input and integrate them into one coherent picture of the world. It makes the car's perception much more robust.
Okay, that makes a lot of sense. So the agent has sensed the world, cleaned up the data, fused it all together into a coherent picture. Now it needs to decide what to do. That's the plan part, right? Reasoning.
Precisely. Reasoning. This is the agent's brain, its core intellectual capability. Reasoning is where the agent takes that perceived information, combines it with its existing knowledge base and its overall goals, and uses that to infer new information, draw conclusions, and make predictions about what might happen next.
And this reasoning drives the decisions.
Correctly. The entire process of reasoning is geared towards figuring out the best course of action to take in the current situation to achieve its goals.
Are there different kinds of reasoning that AIs use?
Yes, we can categorize them broadly. One fundamental type is deductive reasoning. This is about drawing conclusions that are logically certain given a set of starting premises or facts. If you know A is true, and you know if A then B is true, you could deduce with certainty that B must be true.
Like logical proof.
Exactly. For example, an agent managing a warehouse might have in its knowledge base the rule, all refrigerated storage units require temperature monitoring. If it then perceives that Unit 4B is a refrigerated storage unit, it can deductively conclude with 100% certainty that Unit 4B requires temperature monitoring. This kind of logical certainty is crucial for ensuring reliable and safe operation in many tasks.
Okay, so deductive gives certainty. What's the alternative?
The counterpart is inductive reasoning. Here, the agent draws general conclusions based on specific observations or patterns it has seen in the data. These conclusions are likely to be true or probable, but they aren't logically guaranteed like deductive conclusions.
So it's more about finding trends.
Finding trends, making generalizations. For example, an e-commerce agent might observe that 90% of customers who bought product X also bought product Y in the past month. Based on this pattern, it might inductively conclude that future customers buying product X are highly likely to be interested in product Y. This is the basis for recommendation engines, but it's a probabilistic conclusion, not a certainty. Someone buying X might not want Y.
Gotcha. Deductive is definite, inductive is probable. So once the agent has its goals and understands the situation through reasoning, how does it figure out the actual steps to achieve those goals? Like, how does it find the path?
Right. That's where search algorithms come into play. Once an agent have a goal, whether it's navigating a robot to a specific coordinate, finding the solution to a puzzle, or figuring out a sequence of actions for a complex task, it needs a systematic way to explore the possible sequences of actions or states to find a path that leads to that goal.
Are there simple search methods?
Yes. Foundational algorithms include breadth-first search, BFS, which explores the search space level by level. It's guaranteed to find the shortest path in terms of the number of steps, if one exists, but it can be slow if the solution is far away. Then there's depth-first search, DFS, which explores one path as deeply as possible before backtracking. It's often faster to find a solution, but not necessarily the shortest or best one, and it can get lost down very long paths.
So these are basic, maybe less efficient.
They can be, especially in very large, complex search spaces like real-world robotics or game playing. That's why more intelligent search algorithms were developed.
Okay, like what?
The star, really, in many AI planning applications is the A search algorithm, often pronounced A star.
A star. What makes it smarter?
A is what we call an informed search algorithm. Unlike BFS or DFS, which explores somewhat blindly, A uses a heuristic function. A heuristic is essentially an educated guess or an estimate of the cost or distance from the current state to the final goal.
So it has some idea of how close it's getting.
Exactly. A evaluates each potential path or state based on two things: the actual cost incurred so far to reach that state, and the estimated heuristic cost remaining to get to the goal. It then prioritizes exploring the paths that have the lowest combined cost, actual plus estimated. This means it focuses its search effort on the most promising paths first, the ones that seem to be leading efficiently towards the goal, rather than wasting time on paths that are already long or seem to be heading in the wrong direction.
Can you give an analogy for A?
Think of using a smart GPS navigation app. It doesn't just consider the distance you've already driven, the actual cost. It also uses traffic data and map information to constantly estimate the remaining time or distance to your destination, the heuristic. It uses this estimate to guide you onto routes that appear to be the fastest overall, intelligently avoiding routes that might look short initially but are predicted to have heavy traffic later. A works in a similar way, using its heuristic guess to explore the search space much more efficiently.
That makes a high sound really powerful for planning complex actions.
It is. It's widely used in robotics for pathfinding, in games for character movement, and in many other planning problems, where finding an optimal or near-optimal solution efficiently is crucial.
Okay, so the agent has sensed, it has planned using reasoning and search.
Hmm.
Now it needs to actually do something. That's the act part of the loop, action.
Exactly. Action. This is where the agent exerts its influence on the environment. It's the phase where the plans generated during reasoning are translated into concrete steps that change the state of the world, either physically or virtually.
And how does it perform these actions? What enables it to interact?
Through actuators. Actuators are the components that allow the agent to perform actions. They are the muscles of the agent, if you will. Sure. In a robot, actuators would be things like motors that move its joints or wheels. In a smart home agent, actuators could be the switches that turn lights on or off, the mechanism that adjusts the thermostat, or even speakers that produce synthesized speech. In a software agent, an actuator might be the command it sends to place an order on a website, or the signal it sends to block network traffic in a cybersecurity context. It's whatever allows the agent to make a change.
And are actions all the same, or are there different types?
We can generally classify them. Discrete actions are distinct, usually finite choices, like a robot in a grid world moving left, right, up, or down, or a light switch being on or off. Continuous actions, on the other hand, involve choosing a value from a range, like adjusting a robot motor speed smoothly between 0% and 100%, or setting a thermostat to any temperature within a specific range, say 68.5 degrees. Continuous actions allow for more fine-grained control.
Okay. And how does the agent control these actuators to make sure the action is performed correctly? Are there different control methods?
Yes, broadly two main approaches. The simpler one is open-loop control. Here, the agent sends a command to the actuator based on its plan, but it doesn't use any feedback to check if the action was successful or accurate.
Like just shouting an order and hoping for the best.
Kinda, yeah. For example, telling a motor, run at 50% power without actually measuring if it is running at 50% speed. It's simple, but it's not very accurate or robust. If there's unexpected resistance, the motor might run slower and the agent wouldn't know.
So the better way is?
Closed-loop control, also known as feedback control. This is much more sophisticated, but also much more accurate and reliable. Here, the agent uses sensors to continuously monitor the result of its action and compares it to the desired outcome. It then adjusts the command sent to the actuator based on the difference, or error.
Can you give an example of closed loop?
Sure, think of cruise control in a car. You set the desired speed, the goal. The system uses a speed sensor, feedback, to measure the car's actual speed. If the actual speed is lower than the set speed, for example going uphill, the controller increases the engine power, adjusts the actuator. If it's too high going downhill, it reduces power or applies brakes. This continuous loop of sensing, comparing, and adjusting keeps the car at the desired speed despite changes in the environment like hills. That's closed-loop control, and it's essential for precision in dynamic situations.
Got it. Open loop is fire and forget. Closed loop uses feedback to adjust. So let's tie sense, plan, act all together again with maybe that smart home energy example you mentioned. How does the SPA loop work there?
Okay, perfect. So the agentic smart home energy system, it continuously senses its environment. Thermostats report room temperatures, light sensors measure brightness, occupancy sensors detect if people are in rooms, maybe it pulls down the latest weather forecast online. That's the perception phase, gathering all that data.
Okay, sensing complete, then plan.
Then it plans. Its reasoning engine kicks in. It processes all that sensor data. It consults its learned knowledge about the occupant's preferences. For example, they like a living room at 70 degrees in the evening. And their typical schedules, they usually leave for work by 8 a.m. It factors in the weather forecast, big heat wave expected this afternoon, and maybe even electricity pricing. Rates are higher between 4 p.m. and 7 p.m. Based on all this, it formulates a plan to minimize energy use while maintaining comfort and respecting constraints. The plan might be pre-cool the house before 4 p.m., then let the temperature drift up slightly during peak hours, keep lights off in unoccupied rooms, close smart blinds on the west side when the sun hits them directly.
That's a complex plan based on lots of inputs.
Exactly. And finally, it acts. It executes that plan using its actuators. It sends commands to the smart thermostat to adjust the temperature set points according to the plan. It signals smart plugs or switches to turn off lights or non-essential appliances in empty rooms. It sends commands to motorized blinds to open or close.
And then the loop starts again.
Instantly. As soon as it acts, the environment changes, temperature adjusts, lights go off. So it immediately starts sensing the new state, planning if any adjustments are needed based on new sensor readings or maybe an updated forecast, and then acting again. This continuous sense plan act cycle allows it to intelligently and autonomously manage the home's energy, constantly learning and optimizing over time. It's a dynamic, ongoing process.
That really brings the SPA loop to life. Okay, so now that we have a pretty solid grasp on what agentic AI is, its key features, and the nuts and bolts of how it works through Sense Plan Act, let's maybe take a quick step back and look at its history. How did we get here? This didn't just appear overnight, right?
Not at all. Understanding the evolution is really important. It helps us appreciate the breakthroughs and also some of the recurring challenges. The journey goes from early, very constrained rule-based systems to the much more flexible, autonomous intelligence we're seeing emerge now.
Where does the story officially begin? Is there a starting point?
The generally accepted formal birth of AI as its own academic field is the Dartmouth Workshop in the summer of 1956. This wasn't just a regular conference, it was a truly pivotal event. A small group of brilliant researchers, names like John McCarthy, who actually coined the term artificial intelligence, Marvin Minsky, Herbert Simon, Alan Newell, Claude Shannon, gathered at Dartmouth College for several weeks.
What was their goal?
Their incredibly ambitious proposal was to explore the idea that, and I'm paraphrasing here, every aspect of learning or any other feature of intelligence could, in principle, be so precisely described that a machine could be made to simulate it. They wanted to seriously discuss creating machines that could actually think. It really laid the intellectual foundation for decades of AI research that followed.
Wow. So what came out of that early excitement? What were the first AI programs like?
In that exciting period, the late 50s and into the 60s, we saw some really groundbreaking programs. Two of the most famous were the Logic Theorist and later the General Problem Solver, GPS, both developed primarily by Newell and Simon.
What do they do?
Logic Theorist was designed to mimic human problem solving in the domain of formal logic. Its big claim to fame was proving dozens of theorems from Whitehead and Russell's Principia Mathematica, a foundational work of logic. For a computer program in the 1950s, that was astonishing.
That sounds impressive. And GPS.
GPS, the general problem solver, aimed to be, well, more general. It tried to simulate human problem-solving strategies across a wider range of tasks, not just logic proofs. It worked by comparing the current state to the goal state and identifying differences, then applying operators, actions to reduce those differences. It relied heavily on symbolic reasoning, manipulating abstract symbols according to logical rules. These programs really show the potential of AI for tackling complex intellectual tasks that were previously thought to be exclusively human.
Were there other notable early programs?
Oh, yes. Another really fascinating one was ELIZA, created by Joseph Weizenbaum at MIT in the mid-60s. ELIZA was an early natural language processing program specifically designed to simulate a Rogerian psychotherapist.
Simulated therapist. How?
It used clever tricks, mainly pattern matching and keyword substitution. If you type something like, "I am feeling sad," ELIZA might recognize the pattern "I am feeling X" and respond with something like, "How long have you been feeling sad?" Or, "Why do you tell me you are feeling sad?"
So it looked like it understood.
It created an incredibly compelling illusion of understanding and empathy. People actually got quite attached to it. But Weizenbaum himself was quick to point out that ELIZA didn't understand a single word of the conversation in any meaningful way. It was just manipulating text based on predefined scripts and rules.
So it highlighted the challenge of true understanding.
Absolutely. ELIZA was a technical marvel for its time, but it starkly illustrated just how incredibly difficult genuine natural language understanding, grasping meaning, context, intent really was, and frankly still remains a major challenge for AI today. It showed how easy it is to mistake pattern matching for actual intelligence.
Okay, so after those early symbolic approaches, what came next? I think I've heard of expert systems.
Yes. Moving into the 1970s and peaking in the 1980s, we saw the rise of expert systems. This was a really significant development in applied AI. The core idea was to capture the specialized knowledge of human experts in a specific narrow domain like medicine or geology and encode it into a computer system, usually as a large set of if-then rules.
So bottling up human expertise.
Exactly. The goal was to create systems that could solve problems or give advice within their specific domain at a level comparable to, or sometimes even better than, a human expert. They typically consisted of a knowledge base containing the facts and rules, and an inference engine, which applied the rules to specific situations.
Were there successful examples?
Oh yes, several became quite famous and demonstrated real value. MYCIN, developed at Stanford in the 70s, was a landmark medical expert system. It was designed to diagnose bacterial infections like meningitis and recommend appropriate antibiotic treatments. And evaluations that performed as well as or better than many human infectious disease specialists, which was a huge deal.
Wow, in medicine that early.
Yeah. Another was Dendrol, also from Stanford, which was one of the earliest expert systems. It focused on chemistry, specifically identifying the molecular structure of unknown organic compounds from mass spectrometry data. And perhaps the most commercially successful one was XCON, originally called R1, developed for Digital Equipment Corporation, DEC.
What did ESCON do?
It configured complex VAX computer systems. Back then, ordering a large computer system involved choosing from hundreds of components that had to be compatible. It was a really tricky task that required specialized human experts. XCON automated this configuration process, reportedly saving DEC millions of dollars a year and proving that AI could deliver tangible business value.
So expert systems seem like a big success, but you mentioned their rise and fall earlier. What were their limitations?
Right. While expert systems were a crucial step and had significant successes in specific niches, they had fundamental limitations that eventually led to a decline in enthusiasm, sometimes called the AI winter in the late 80s and early 90s. The biggest issue was the reliance on explicitly programmed rules.
They were too rigid.
Exactly. They were often described as brittle. They worked well within their very narrow, predefined domain where the rules applied. But if they encountered a situation not explicitly covered by their rules, or if the information was incomplete or slightly ambiguous, they often failed completely, sometimes in nonsensical ways. They couldn't handle novelty or uncertainty gracefully.
They couldn't learn or adapt.
No, not really. Building the knowledge base by interviewing human experts and encoding their knowledge into rules was also incredibly time-consuming and expensive. This was called the knowledge acquisition bottleneck. And crucially, they lacked the ability to learn from experience, to adapt to changing circumstances, or to exhibit the kind of proactivity and true autonomy we expect from agentic AI today. They were powerful calculators within their domain, but they weren't truly intelligent in a flexible, adaptive sense.
So that brittleness, that lack of adaptability, that's the key difference compared to modern agentic AI.
It's a huge part of it. Modern agentic AI, especially systems using machine learning, are designed to learn from data, adapt to new situations, handle uncertainty, and operate with much greater autonomy and proactivity. They aim to overcome that brittleness.
Can we connect this back to the smart home energy example?
Mhm.
How would an expert system approach that compared to the agentic system?
Good way to contrast. An expert system for home energy might just have a few simple hard-coded rules like, if temperature 75 degrees air and AD time is between 1 p.m. and 5 p.m. AD occupancy detected, then turn on AC to 72 degrees air.
Very specific, very rigid.
Exactly. It's purely reactive based on current conditions matching the rule's premise. It can't learn your preferences. It can't anticipate a heat wave from a forecast. It can't optimize based on electricity prices unless explicitly told to via another rule. It's just following static instructions.
Whereas the agentic system,
The agentic system, as we discussed, learns patterns, predicts future states, proactively adjusts settings based on forecasts and learned preferences, and dynamically optimizes across multiple factors: comfort, cost, occupancy. It's a fundamentally different, more intelligent and adaptive approach. That evolution from rigid rules to dynamic learning autonomy is really the core story of AI's progress towards agentic capabilities.
okay, that historical context is really helpful. It shows how far things have come. So let's pivot back to the present and look towards the future. We've talked about what agentic AI is, how it works, and its roots. Where are we seeing it make a real difference today, and what might be coming next?
The applications are becoming incredibly diverse and honestly quite transformative across many different sectors. It's moving out of the lab and into the real world.
Like where specifically?
Well, take agriculture. We touched on this briefly. Agentic AI is powering robots like those from Blue River Technology, which is now part of John Deere. These aren't just dumb machines, they're autonomous agents.
Doing what exactly?
They use sophisticated computer vision, their perception system, to drive through fields and identify individual plants. They can distinguish between crops and weeds with incredible accuracy down to the single plant level.
Okay, they can see the weeds. Then what?
Then they use their actuators, precision spray nozzles, to apply a tiny amount of herbicide only to the weeds, not the crops or the surrounding soil. It's called precision spraying or spot spraying.
Instead of spraying the whole field.
Exactly. Instead of blanket spraying, which is the traditional method, the benefits are huge. It dramatically reduces the amount of herbicide used, sometimes by up to 90%.
Wow, that must be great for the environment.
Absolutely. Less chemical runoff into waterways, healthier soil. Plus, it saves farmers a lot of money on chemicals and can lead to better crop yields. It's a fantastic example of an agent autonomously perceiving, deciding, weed or crop, and acting precisely for both economic and ecological benefit.
That's genuinely impressive. What about a completely different field, like finance?
Oh, finance is a huge area for agentic AI, particularly in financial trading. There are autonomous trading agents, sometimes called algo trading bots, but the sophisticated ones are truly agentic.
How do they work?
They continuously sense the market by ingesting massive, real-time streams of data, stock prices, trading volumes, order book data, news feeds, social media sentiment, economic reports, you name it.
That's a lot of data.
An overwhelming amount for a human. The agent's reasoning engine analyzes all this, looking for complex patterns, correlations, anomalies, trying to predict short-term market movements. Then, based on its predictions and program trading strategies, it autonomously acts by executing trades, buying or selling assets, often at incredibly high speeds, far faster than any human could.
All to maximize profit.
Maximize profit and manage risk according to its goals. It's a very high-stakes, high-speed environment where the agent's autonomy, proactivity, acting on predicted movements, and reactivity, adjusting to sudden market shifts, are absolutely paramount.
Okay, another critical area, cybersecurity. How are agents used there?
Agentic AI is becoming a vital tool in defending networks and systems. You can think of these AI agents as autonomous digital guardians.
What do they guard against?
They continuously monitor network traffic, system logs, user activity patterns, sensing the digital environment. They're looking for anomalies, suspicious behaviors, patterns that match known attack signatures, or even novel threats that don't fit normal patterns.
And when they find something?
They can reason about the potential threat level and then act autonomously. This might involve blocking malicious IP addresses, isolating compromised machines from the network to prevent an attack from spreading, alerting human security analysts, or even deploying countermeasures. Their ability to react at machine speed 247 is a huge advantage over purely human monitoring. They are proactive in hunting for threats and reactive in neutralizing them.
Makes sense. What about something maybe more people interact with directly? Customer service.
Definitely. Customer service chatbots and virtual assistants are probably one of the most common encounters people have with systems that are becoming more agentic.
Becoming, so they're not fully there yet.
Many are still fairly simple, rule-based, or retrieval-based, but the more advanced ones are incorporating more agentic capabilities. They're getting much better at understanding the nuances of natural language queries, perception. They can access and reason over vast knowledge bases to find relevant answers, planning reasoning.
Can they learn?
Some are starting to. They might use techniques like case-based reasoning, where they learn from past successful interactions to handle similar problems in the future. They can personalize responses based on customer history. The goal is to move beyond simple FAQ bots to agents that can actually understand context, manage dialogue over multiple turns, and genuinely solve customer problems autonomously. Action. We're seeing rapid progress here.
And physical robots, besides the farming ones.
Oh, absolutely. Robotics is a natural home for agentic AI. We mentioned the Roomba vacuum cleaner earlier. That's a classic example of behavior-based robotics, a type of agent architecture. It uses simple rules and sensors to navigate autonomously, clean floors, avoid obstacles, and find its charging dock. It perceives, plans its path locally, and acts.
Any more complex examples?
Historically, the NASA Mars rovers, like Sojourner back in the 90s, or Spirit and Opportunity later on, were amazing examples of autonomous agents operating under extreme conditions. Because of the significant communication delay between Earth and Mars, they couldn't be remote controlled in real time.
Right, the signals take too long.
Exactly. So the rovers had to have onboard autonomy. They could perceive the terrain ahead with cameras and sensors, analyze risks, like big rocks or steep slopes, plan safe paths to navigate around obstacles, and then execute those driving commands all on their own, millions of miles from Earth. That required sophisticated perception, planning, and action capabilities built into the agent itself.
That's incredible. Looking even further ahead, what's the big vision? Could agents manage whole systems?
That's definitely where some researchers and futurists see things heading. Imagine agentic AI operating at the scale of an entire city.
Managing a city? How?
Think about urban management. You could have sophisticated AI agents optimizing traffic flow across the entire city in real time, sensing congestion using road sensors and vehicle data, predicting traffic jams before they happen, and proactively adjusting traffic light timings, suggesting alternate routes to drivers via navigation apps, maybe even coordinating public transport schedules dynamically.
That would be amazing. What else?
Maybe managing the city's energy grid. Agents could predict energy demand based on weather events and historical patterns, then optimize the generation and distribution of power, integrating renewable sources like solar and wind more effectively, and maybe even incentivizing residents to shift energy use away from peak times through dynamic pricing communicated by home agents.
Resource allocation, too.
Potentially. Managing water resources, optimizing waste collection routes based on sensor data from smart bins, coordinating emergency response services more effectively during incidents. The vision is for a network of interconnected agents working together to make cities more efficient, sustainable, responsive, and ultimately better places to live. It's a huge, complex challenge, but the potential benefits are immense.
It's a fascinating, if slightly daunting, vision. But with all this power and autonomy, there must be significant concerns, right? Things we need to get right.
Absolutely critical concerns. As these agents become more capable and more integrated into our lives, we have to address the crucial roles of explainability, bias, and safety. These aren't optional extras. They are fundamental requirements for responsible development and deployment.
Let's start with bias. How can AI agents be biased? I thought they were just math and data.
That's a common misconception. Bias can creep in from several sources. A major one is the data used to train the AI. If the training data reflects existing societal biases or isn't representative of the real-world population the agent will interact with, the agent will likely learn and perpetuate those biases. This is often called data biases or dataset biases.
So if historical hiring data showed fewer women in engineering roles,
An AI trained on that data to screen resumes might learn to associate male candidates with engineering roles and unfairly penalize female candidates, even if their qualifications are identical. It learns the bias embedded in the historical data.
are there other sources of bias besides the data?
Yes. Bias can also come from the algorithmic design itself. The choices engineers make when designing the model, The objective function is trying to optimize. The features it pays attention to these can inadvertently favor certain outcomes or groups over others. That's algorithmic bias.
And humans involved.
And of course, the human developers and users can introduce bias, consciously or unconsciously. Their own assumptions, perspectives, and blind spots can influence how the system is designed, tested, deployed, and interpreted, even with the best intentions. It's a really complex, multi-layered problem.
What are the real-world consequences of this? You mentioned hiring.
The implications are huge and potentially harmful. Biased AI agents could lead to unfair discrimination in hiring, loan applications, access to housing, medical diagnosis, even criminal justice sentencing if predictive policing tools are used. It can reinforce and even amplify existing societal inequalities. This raises a really important ethical question. How do we proactively design and audit these systems to ensure fairness and equity are core principles, not just afterthoughts? It requires careful thought about data collection, algorithm design, testing, and ongoing monitoring.
Which leads directly to explainability and transparency, doesn't it? If we don't know why an agent made a decision, it's hard to tell if it was biased or just wrong.
Exactly. Explainability, sometimes called interpretability or XAI, explainable AI, is crucial for building trust, especially in high-stakes applications. People affected by an AI's decision, whether it's a doctor using an AI diagnostic tool or a person denied a loan by an automated system, need to be able to understand how and why that decision was reached.
But isn't that hard with complex AI, the black box problem?
It is a major challenge, especially with complex models like deep neural networks. Their internal workings involve millions or billions of parameters interacting in nonlinear ways, making it incredibly difficult for humans to follow the exact reasoning path. It's like trying to understand how a brain thinks by looking at individual neuron firings. You lose the big picture. This opacity is the black box problem.
So how do we get explanations?
For simpler models, like traditional rule-based expert systems or decision trees, explainability is often built in. You can literally trace the rules or the tree branches that led to the decision. But for the complex black box models, we often rely on post hoc explanation techniques. These methods don't try to fully understand the model's internal logic, but rather they probe the model after it makes a prediction to understand what drove that specific prediction.
Can you give examples of those techniques?
Two popular ones are LIME, local interpretable model agnostic explanations, and ESHAPE, Shapley additive explanations. LIME works by creating simpler, interpretable models that approximate the behavior of the complex model locally, just around the specific prediction you want to explain. ESHAPE uses concepts from game theory to assign an importance value to each input feature, showing how much each feature contributed to pushing the prediction towards a certain outcome. They essentially try to highlight the key factors the black box considered for that specific decision.
Let's make that concrete. The inventory agent choosing a supplier, how would explainability help there?
Right, so without explainability, the agent just says, switching to supplier B. The human manager is left wondering why. With explainability, using something like FHA, the system might provide a justification like, I selected supplier B primarily because its 10% price discount, feature importance plus 0.5, and its 98% on-time delivery record, feature importance plus 0.3, outweighed supplier A's slightly shorter lead time, feature importance 0.1. The projected outcome is a 5% cost reduction and improves supply reliability.
Ah, okay. That gives a clear rationale.
Exactly. It provides transparency, builds trust, allows the human manager to understand the trade-offs the AI made, and enables them to potentially override the decision if they have other contextual information the AI might lack. Explainability is key for effective human-AI collaboration and oversight.
Okay, so bias and explainability are crucial. What about just basic safety and robustness, making sure these things don't cause harm or breakdown?
Absolutely fundamental. Safety is paramount. It's about designing the agent specifically to prevent it from causing harm to individuals, property, or the environment. This involves building in constraints, safeguards, and fail-safe mechanisms.
Like the thermostat limits you mentioned.
Exactly. Setting hard limits on actions, like a smart thermostat not going below 65 degrees ARA or above 78 degrees ARA without explicit confirmation. Or ensuring that an AI controlling physical machinery has emergency stop procedures. Critically, it means not giving full autonomous control to AI in situations where failure could have catastrophic consequences, like controlling life support systems without rigorous testing, validation, and robust human oversight and override capabilities. Safety has to be designed in from the start.
And robustness, that's about handling errors.
Robustness and reliability are about ensuring the agent can perform correctly and consistently, even when things aren't perfect. Can it handle unexpected events or inputs gracefully? Can it recover from internal errors or sensor failures without causing problems? Can it operate reliably even when its sensor data is noisy, incomplete, or uncertain?
Like the self-driving car needing to handle a sudden obstacle.
Precisely. Or a manufacturing control agent needing to diagnose a machine malfunction, even if some sensor readings are ambiguous. Robustness is about making the agent resilient to the messiness and unpredictability of the real world. And closely related is security.
Protecting the agent itself.
Yes, protecting the agent from malicious attacks. Adversaries might try to fool its perception systems with manipulated inputs, so-called adversarial examples, exploit software vulnerabilities to take control, or poison its training data to make it behave incorrectly. Ensuring the security of the agent itself is vital, especially for agents controlling critical infrastructure or handling sensitive data, like a financial fraud detection system needing to resist attempts to manipulate transactions to evade detection.
Wow, there's a lot to consider beyond just making the AI smart. So, looking ahead, what are the big research challenges? Where is the field pushing forward?
There are several major frontiers. One huge ongoing challenge is simply scalability and complexity. While we can build impressive agents for specific tasks, scaling them up to handle the sheer complexity, dynamism, and scale of many real-world environments remains incredibly difficult.
Like this city management example.
Exactly. Coordinating hundreds of thousands of autonomous vehicles, managing a power grid with millions of fluctuating inputs and outputs, dealing with the near-infinite variability of human behavior. The computational complexity, the communication overhead, the potential for unintended interactions between agents. These are massive scaling challenges that researchers are actively tackling.
And building on the previous point, robustness and reliability remain a huge focus.
Absolutely. How do we make agents provably robust against unforeseen circumstances or adversarial attacks? This involves research into handling uncertainty more effectively, maybe using probabilistic methods that reason about likelihoods rather than certainties. Developing better techniques for automatic error detection, diagnosis, and self-recovery is crucial. And the arms race against adversarial attacks requires continuous innovation in defensive techniques. It's about building trust through demonstrable reliability.
What about the interaction with humans?
That's becoming increasingly central. There's a strong push toward human-centered agentic AI. This research focuses on how to design agents that can collaborate effectively with humans, augmenting our abilities rather than just replacing us. It involves improving communication between humans and agents, making agent behavior more predictable and understandable, and designing intuitive interfaces for interaction and control.
And the ethical alignment part.
Yes, a critical component of human-centered AI is value alignment. How do we ensure that the goals and behaviors of increasingly autonomous agents align with human ethics, societal norms, and fundamental values? This is a deeply challenging area, involving fields from computer science to philosophy and sociology. How do you formally specify complex human values like fairness or well-being in a way an AI can understand and optimize for? It's a crucial long-term research direction.
You also mentioned embodied AI earlier. Is that a big trend?
It's a very exciting and growing field, yes. Embodied AI focuses on agents that have a physical body, usually robots, and learn through direct interaction with the physical world via sensors and actuators.
Why is embodiment important?
The hypothesis is that interacting with the real physical world, dealing with physics, friction, object permanence, the consequences of actions, forces the AI to develop a deeper, more grounded understanding of how the world works. This might be key to developing genuine common sense reasoning, something that purely text-based or simulation-based AIs often struggle with. Learning by doing, literally.
And finally, what about the learning aspect itself? Is AI getting better at learning continuously?
That's perhaps one of the most transformative research directions. Continuous learning. This addresses a major limitation of many current AI systems, which are often trained once on a large data set and then deployed, without the ability to keep learning and adapting afterward.
So continuous learning aims to fix that.
Yes. One area is lifelong learning. The goal here is to create agents that can continuously learn from new experiences throughout their operational lifespan, accumulating knowledge and skills over time without forgetting what they've already learned. This challenge of forgetting old knowledge when learning new things is called catastrophic forgetting, and overcoming it is key for truly adaptive agents.
Okay, learning without forgetting. Is there anything beyond that?
Yes, perhaps the most ambitious goal is meta-learning, which is often described as learning to learn.
Learning how to learn.
Exactly. Instead of just learning a specific task, meta-learning agents aim to learn more general strategies or processes for learning itself. This allows them to adapt much more quickly and efficiently to entirely new tasks or environments, often with very little new training data.
How might that work?
Imagine an investment agent. Instead of just learning a strategy for today's market, a meta-learning agent might learn general principles about how to quickly identify and adapt to new types of market dynamics, or entirely novel financial instruments it's never seen before. It learns the process of adaptation itself, making it incredibly flexible. It's like teaching an AI student how to become a quick study, enabling it to generalize its learning capabilities to brand new situations. This could be key to creating truly general-purpose, adaptable AI agents in the future.
Wow, what an incredible journey we've been on today. We really have dug deep into agentic AI. We started right at the core, defining it as this autonomous, goal-driven entity.
Right, distinguishing it from just reactive systems by focusing on that autonomy, that proactivity, the looking ahead, alongside its necessary reactivity.
And those analogies, the smart home, inventory management, even personalized education, I hope those help make the concepts really click for you, our listeners. We definitely had some aha moments ourselves just talking through them.
Then we pulled back the curtain on the mechanics, didn't we? That
Yeah.
fundamental sense-plan-act loop. We looked at perception, the sensors, the crucial need for pre-processing and sensor fusion to build that world model.
Followed by reasoning the agent's brain using deduction and induction, and those clever search algorithms like A to figure out the how. And finally, action using actuators and control loops to actually impact the world.
And the history. From Dartmouth and those early pioneers like logic theorist and the fascinating Eliza, through the rise and limitations of the rule-bound expert systems, seeing that evolution really highlights the leap to today's more adaptive learning agents.
Absolutely. Then we toured the real-world applications that are already here. Precision agriculture, high-speed trading, cybersecurity defense, improving customer service, robotics from Mars rovers to Roombas, and that glimpse into future possibilities like managing entire cities.
But always keeping in mind those critical guardrails. Tackling bias in data and algorithms, striving for explainability to build trust, and ensuring safety, robustness, and security are paramount.
Before finally touching on the cutting-edge research, the challenges of scale, the quest for robustness, the importance of human-centered design and value alignment, the potential of embodied AI, and the exciting frontier of continuous and meta-learning.
It really hammers home the point that agentic AI isn't some far-off sci-fi concept anymore. It's here. It's a rapidly expanding reality, already woven into so many industries, often behind the scenes, constantly sensing, planning, acting, and increasingly learning.
Which brings us to a final thought, maybe something for you to mull over after this deep dive. We've talked a lot about agents that learn, adapt, operate autonomously in ways we don't explicitly program step by step. So, as these AI agents become increasingly capable, continuously learning and evolving, how might our own definition of intelligence need to evolve alongside them?
That's a deep one. What does it truly mean for us to interact with systems that aren't just tools, but entities that learn, adapt, and maybe even anticipate our needs in ways we haven't fully grasped yet?
A fascinating question indeed. We really hope this exploration has not only informed you, but also sparked even more curiosity about this incredibly dynamic field.
Keep exploring, keep questioning. The world of agentic AI is only going to get more interesting.
Thanks so much for joining us on the deep dive.